and welcome back to AGT STEM. Today we're going to be watching a video about zirconium. So, without further ado, let's hop to it.
From time to time, people give me samples of elements, but it's not very often that I get two samples, and even rarer that I get two samples that are very different. But with zirconium, I've had one sample which is big lumps of metal. This comes from a company that supplies large quantities of specialist metals to customers. The other sample is a very fine powder of zirconium, which was sent to me by a technician at St Paul's School in London. And I've given the powder sample to Neil to see what he can do with it.
So Neil, what are you going to do with this powder?
This sample is interesting, first of all, because it's relatively light. Zirconium is in the middle of the periodic table, and so although these look large lumps, they're not very heavy.
Can I feel? Yeah.
Zirconium has one particular application, which is it is used for cladding of nuclear fuel in nuclear reactors. These samples came from Russia, which specialize in making zirconium. In fact, you may have seen from some of my earlier videos, I have a vodka glass also made from zirconium. Well, it's not a glass, it's a vodka container, and when I need cheering up, I drink from it. But the big problem
It's another element that looks like a firework when you sprinkle it into a flame.
Of zirconium is separating it from hafnium. So with my sample came a really quite comprehensive analytical data of all the different elements that they've tested for. And if you look down, these numbers here in the columns are in parts per million. And they're all very, very small. There's a tiny amount of tellurium or barium or neodymium. But when you get to hafnium here, it's got really quite a lot, 250 parts per million. And the reason why you need to purify the hafnium is because in nuclear applications, hafnium can absorb neutrons and therefore could spoil the behaviour of the fuel in a nuclear reactor. It's hard to separate because hafnium and zirconium are in the same group of the periodic table and their chemical properties are very similar. When two elements have similar chemical properties, they're always hard to separate.
It's pretty bright, like a little too bright, the little lights.
Nice.
The fuel in a nuclear reactor is usually some form of uranium oxide, which cannot be made into nice rods. So you put them essentially into a can, rather similar to my vodka glass, but a long tubular can, which gives them the mechanical rigidity so you can lower them in and out of the nuclear reactor. The outer coating is made out of zirconium. The problem comes when things go wrong in the nuclear reactor, because at very high temperature, zirconium can react with the steam in the nuclear reactor. The steam comes from the water that is used to cool the reactor, and zirconium can extract the oxygen from water to make zirconium oxide and hydrogen. So you can generate zirconium oxide, which causes the fuel rods to start falling to bits, and at the same time hydrogen, which can mix with air and explode. And you will have seen pictures of exploding nuclear reactors, for example, Chernobyl.
If the zirconium reacts with the steam, then it's just a whole mess. It's chaos.
Or more recently at Fukushima, because of this reaction between fuel, cladding, and steam.
Why don't we not use zirconium in our cladding?
Well, zirconium has the right properties to, from the nuclear point of view, and many other elements also react with steam at high temperature. Iron does, for example. And iron rusts as well, so that would be even more problems. So you can't get round the fact that most metals at high temperature will form oxides. Zirconium oxide is actually quite an abundant material. Apparently, there's some beaches in Australia, in the northern part, which are, the sand is mostly zirconia, so it's zirconium oxide. So it's a really quite abundant.
That's interesting. They have beaches in Australia that are full of zirconium.
Abundant element. So it's not going to be one that is going to run out very soon compared to some of the other really rare elements.
Thank you so much for watching. We'll see you next time. Stay smart. Bye.